Do you know what we're doing here? All right, does anyone else need the 11.8, 11.10 handout, the Power Series stuff? Sure. Okay. No questions on homework? Even though some of them are very strange? Okay. All right. Okay. All right, well, let's get back into where we left off last time, which was Power Series, right? So today what we're going to do is we're going to kind of explore Power Series a little bit more, because I think last time we just barely started to step into them. And then I want to, so Power Series, the first thing we do is just to familiarize yourself with what the hell they are, what are the components, can you construct your own? And then we're going to ask, are they really good for anything? Which is always a good question, right? So they exist, yay. We can do shit with them, yay. Can we do, like practical, useful shit with them? That's a really good question, right? So that would be the next level of this. So can anyone, well, you've only got your thing, but what are the components of a Power Series? In fact, it kind of explains why it's called a Power Series. Does anyone?
Constant.
It's got a constant piece. And can anyone explain to me why it's got the little subscript? All right, we'll talk about that in a minute. So it's got a constant piece. It's a constant, but that doesn't mean it's the same number for every term. So it's a constant that is a function of n, which is hilarious. It's sort of like a straight angle. So it is a constant that is a function of n. Okay. So we'll talk more about that in a minute. And then what makes it a Power Series is the fact that you have x to the n power. So let me do this. Let me remind you guys about something. We actually know something about this series. All right. So what I really want you to pay attention to is this is a function of x. Do you guys see that? It's not a function of n, even though n changes amongst the terms, right? It's not a function of n because what controls n? This shit does. I don't get to control n. N is already controlled. You guys see what I mean? Like here, I could put f of 7. And that would be this, is it? 7 to the n. In fact, let me be more specific. Oh yeah, I didn't put it there. Let me make Cn 1, like I got there, right? So if this is f of x, f of 7 would be this. Can anyone tell me anything about that?
Divergent.
Why?
Geometric.
All right, sweet. Two beautiful things. It's geometric. Somebody with it? Right? It doesn't look like a normal geometric because what I'm used to seeing for geometric would be some kind of a fraction because then it has a chance to converge. This definitely diverges. Somebody else tell me exactly why this diverges.
Is this greater than 1?
Yeah, R is 7, which is greater than 1. Oh shit. And so it diverges, right? I'm going to add 7, 1 to 7 to 49. No, that's not going to, that's going to go to infinity pretty quickly. So help me out. What about this? Can you take a minute and tell me everything you can? Nobody say anything right now. Just think about everything you can tell me about, no, you're right. Just tell me everything you can about the resultant series from this. Write it down. You should be able to tell me a couple of really key things. So write down what that series would be, right? If this is f of x, what would that series be? And then tell me whatever the hell you can about it. Yeah, so it converges y.
R is less than 1.
R is 1/5, less than 1. What else can you tell me? Something you normally can't tell me about most series.
You can tell what it converges
You can actually
to.
tell me what the hell this adds up to be, right?
Mhm.
What's the first term?
1.
Yeah, and a 0, I get 1 over 1 minus r, right?
Mhm.
So what's that?
5 over 4.
5 over 4. Do you guys agree with me that this shrinks pretty quickly? You guys agree? So let's just do one more thing. One more little thing. This is a total side note. Little review. Can anybody please tell me for this series here? So this is A, this is B. So this is B part 1. B part 2 is, what is S5? So with most of mathematics, when you have a symbol question, you have to say, what the shit does the symbol mean? What is it really asking me? What's the question that the symbol embodies, right? So what does S sub 5 represent?
S1 plus S2.
Yeah, the fifth, not S1 plus S, but
A1.
the fifth partial sum, so A1 plus A2, yeah. So this would be A1, well, what's A1? 1. What's A2? 1/5. What's A3? Yeah, just keep multiplying by 5 on the bottom, right? Plus 1 over 125, plus 1 over 625. 1, 2, 3, 4, 5. Yeah, that's a little bit weird, but that's 0, but screw it. S5 is the first 5 terms, right? So let's see, what will this be? Whatever the hell it is, I don't know. This is like 1.2, what is it? Yeah, 1.2, 4 stuff. I don't know what you get. You guys agree? Isn't 1 over 5.2?
Mhm.
Isn't 1 over 25.04? 1 over 25 is 4 over 100.04?
Yeah.
1 over 125. What's that?
1 to 8,000.
wait. So that's 1.24 plus, do it again, what?
Or 0.008.
0.008, I love it. So this would be 1.248, right? Blah, 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 you guys understand what's happening?
Yeah.
And then 1 divided by 625, I can tack that on. What is 5/4 as a decimal?
1.6.
1.25, right? 1 1/4. Isn't that already almost 1.25? Now again, a general series sitting there, you can't do this kind of analysis because why does this one make sense? Because I know 1/5 is shrinking pretty damn fast, 1/5 to the end. So it's gonna make the sum pretty quickly. It's gonna get really close because then the infinite number of things after that are just filling in the end. Does that make any sense? So the first few terms, since this thing is decreasing so fast, the first few terms are good enough to estimate what the whole sum is. Because it's going so quickly down. So the next few terms after this, they're like in the 5th, 6th, 7th, 8th decimal place. Which most humans, we don't give a shit about normally, right? Unless I'm measuring gravitational waves because of the collision of black holes light years away. Then I care about the 42nd decimal place at least. Because that's where everything's happening. Okay. Maybe. You guys know about that, by the way? The LIGO, L-I-G-O? Detecting black holes colliding into each other light years away? By measuring the gravitational waves, like reality itself shook for a little bit, and then actually measured that. The LIGO, L-I-G-O. Look it up, kids. Look it up. No, doing quite well. Okay. All right. I was gonna wear this shirt that said, sometimes they go off on a tangent. It's got a picture of a tangent line. So that wasn't totally a tangent. It's just a little review about some of the terminology and some of the ideas. Okay, so coming back to what we care about. This anything that can be put in this form is a power series. So this is a power series. And then I could put whatever I want to in for x and see what happens with the series. Can somebody then tell me, for this power series, this, first off, really easy question. What does Cn equal to? 1. There's a 1 there, right? Now, harder question. What values of x makes this converge? What values of x would cause this to be convergent? And you know already. Why did this diverge? Because x was too big.
So greater than -1, less than 1.
And you can say this.
That was that. Yeah.
Yeah? What if x equals 1? What happens? What kind of series do I get? I'm adding up 1 forever, right? Does that converge? No. What about if x is -1?
Still.
What do I get? -1 to the end. What kind of series is that? Alternating, the most basic alternating series. But what's the sum? -1 plus 1 plus -1 plus 1 plus -1. Does that get anywhere in the limit? Never. It can't agree on 0 or -1 or whatever, right? You guys with me? So that also diverges, but for a slightly different reason. Right? Adding 1 forever goes to infinity. Adding -1 to 1 to -1 to 1 doesn't go anywhere. It doesn't actually go somewhere. It's just always boom. Okay, maybe. Okay, so let's do this. I think last time I did a couple of these. Oh, real quick, I'm sorry. Let me go one more step with this, and this is getting a little ahead of ourselves, and I don't care. So this thing, does everyone agree then this is geometric? If the choice I have of inputs is less than 1, then like we said, this converges, correct? Can anyone tell me what it converges to? And you totally can. Sum is a over 1 minus r, correct?
Yeah.
What's the first term? Doesn't matter what x is. What's the first term? 1. And what's r? You do it.
Absolute value of x.
It's x. X is r, right? Okay, let me stop for a minute. Let me just really absorb everything that just happened. Didn't we just remember what I had up here when it was 1/5, right? Didn't we figure out what the sum was? If I made it 2/5, couldn't we figure out what the sum was? Mathematically, shouldn't I be able to create a formula that no matter what the shit x is, as long as it's convergent, I should be able to write that the sum is based on x, correct? So if I had this, and I put 2/5 there, is that the sum? First term is 1, r is 2/5? Yeah, of course. Isn't x r in this?
Yeah.
In this one exactly, right? Not forever, we'll see, but for this one specifically. Let me stop for a minute. Really want you guys with me because this is so cool what we just did. I don't know if you guys understand what we just did. What we just did is this. We just said, what is this equal to again? You tell me what we just said. What is this equal to?
Sum
The sum of what?
of the whole series.
This thing. This is this.
Oh.
If x is, if the absolute value of x is less than 1, right? We just took a function. We didn't do it directly. We will do it directly later, but we kind of did this backwards. We just took a series and represented it as a function. Later, we're going to take a function and represent it as a power series. And of course, we'll talk about doing that, and then we'll talk about why the hell you would want to do that, right? There's always a question in mathematics. Okay, I know how to do that. Why would I want it? Good question. And it's so kick-ass. You don't even know. It's a huge thing. Okay. So what this means is something very freaky. Can somebody tell me? So what this means is that 1 over 1 minus x equals this. Can somebody start telling me some series elements of this? What's the first element? We said it many times. First element, 1. Plus, next element. When n is 0, I get 1. When n is 1,
Get X.
I get x. When n is 2, I get
X squared. X is there. X is
what is this? What would you call it in general? This is an example of a what? Polynomial, right? In fact, how long does it go? Infinitely long. So didn't we just represent a function as an infinitely long polynomial? So a really good question would be, what functions can I represent as infinitely long polynomials? Okay, maybe, right? Why would I want to be able to do that? Because if I just need to be close enough, couldn't I chop this off here? In fact, didn't it just take 1, 2, 3, 4? 4 terms up there, we got 1.248, and the actual answer was 1.25. Good enough for government work, correct? Right? In fact, good enough for most work, right? If you needed to do some math to this, would you rather integrate this, or would you rather integrate this, for example? Yeah. And this is not that hard. It really isn't, but it's a little bit tricky. It's got some chain rule shit and stuff, right? I'd much rather integrate this thing. And then imagine if this is something truly disgusting. And I can make that into a polynomial. And then I can cut it somewhere because I don't need to be perfect. And then I can do math shit to it. I can do calculus to it. What kind of function do you want me to give you to take the derivative and integrate? A freaking polynomial. Or, even better would be 5. It's the derivative of 5, 0. But a polynomial is the next best thing, yes? Yeah. Okay, I really want you all to buy in on the surface why it's neat and possibly very useful to try to take a function and represent it as this infinite polynomial. And again, this line is just saying stop, because it can go forever. And the more precise you need to be, the further out you go. That's it. Okay, maybe. Okay. All right, so let's come back. So that one, I just wanted to talk about that right now because that's sort of like where we're headed, and it comes right off of this beautifully. Okay. So to be really honest, this is where 11.9 starts, but it just comes right off of this. Okay. So let's take it back. Let's step back into 11.8, Jeff. Okay. All right, so let's do this. Can somebody give me, well, let me do this. Let me start off, let me make one myself, because otherwise I'm going to get some really weird stuff. Is that a power series?
Yeah.
Yes. So what C sub n means is for any value of n, is the thing here a constant? Yes. Any value of n you give me, this is a constant. And it starts at 0, which is weird, but I won't do that for everybody. Now, a really interesting question would be, when does this thing converge? And again, I'm getting a little ahead, and I don't really care, because this is built right off of what we just did. I give you any series. What test would you like to use to see when this thing converges? You can do it. See how it's a ratio test. I love it. So, if I ask you, when does this converge? What would the ratio test look like for this? nothing new, it's the same old ratio test. I don't care there's an X, who gives a shit? What does it look like, ratio test?
N+1.
Yeah, so it's the next term, n plus one over,
N+1 squared.
good,
Plus 1.
Yeah.
Times x to the
yeah,
n.
let's do this. Just make it easier to look at, times, right?
The reciprocal.
Yeah, just take this thing, flip it, so it'll be n squared plus one over, n x to the n. So don't freak out about, look at the n's, just the n stuff. N squared, this n cubed, n squared, n, that's n cubed, same degree. So all the n stuff goes to, no, okay, so let's do it more carefully, okay. So let me put this together, so this is n plus one times n squared plus one, I'm just gonna put all the n stuff together. N plus one squared plus one times n. And then you got this business here. Okay. What's the degree of the top? Good. What's the degree of the bottom?
3.
Degrees are the same, so the limit as n goes infinity is equal to the ratio of the coefficients, which is?
1.
Freaking 1, okay, good. All right, so don't let polynomial pieces, those are awesome. You just look at the degrees. If they're the same ratio coefficient, if the bottom's bigger, 0, the top's bigger, infinity, blah, blah. Okay. And of course, what does this reduce to?
X.
Yeah. Now, some people will get here and not know what the hell to do. Now, here's the thing. Whatever that is, what must be true about it? In fact, this limit, of course, is this, isn't it? Because there's no n dependence. So as n gets bigger, x didn't care, right? What's got to be true about whatever the hell we just got?
Has to be less than 1.
It's got to be less than 1. I like it. Now, stop for a minute. So this means, what values of x am I allowed to plug in? Anything from what to what?
Negative 1.
-1 to 1. But, let me remind you guys, what does the ratio test say if the limit is 1? Inconclusive. So, do I know what happens at the endpoints? Because that's when it equals 1, right? I really want you guys to see. When you're testing power series for convergence, you get less than 1, you get this. But then your endpoints, you have to check them. The beautiful thing is, the endpoints are specific. They're not just anything, they're 1 and -1. So if x equals -1, what does my original thing look like? If x equals -1, what does this look like?
Negative 1 to the n.
-1 to the n. What kind of series is that?
Alternate.
Alternating. I'm gonna allow you to show me less work now, because we've done enough, I think, right? But I do want you to mention what has to be true. So for alternating series, what has to be true? Limit is 0. Check, right? That's obviously true. The limit is 0. It's got to be
Decreasing.
decreasing. It's pretty obvious it's decreasing. You guys agree with me, or do you really see that it's obvious? Because the bottom is growing a lot faster than the top. So of course, at some point, it's going to be decreasing. If not immediately, it definitely will forever after some point. And of course, what did we have to do before? We had to do derivative. So now I'm trying to be a little more relaxed about it, right? We've seen enough shit. We should have a better feel for when something's decreasing or when something's whatever. Is that all?
No.
One more thing. What?
A n plus 1 has to be less than.
Well, that's decreasing. Yeah. Positive terms, right? And this is obviously positive terms for n greater than 0, right? Well, as n equals 0, it's 0, but forever after that is positive. You guys agree? So what does that all mean? What's true if x is -1? What does the series do? All those things are true. Therefore, this converges. We'd say conditionally, but yes?
When you said x equals -1, is that going to be a given? Or do you,
I really want this to make sense. So if this is true, it's convergent. Beautiful, right?
oh, okay, yeah, yeah.
But what else does the ratio test say? If this equals 1, inconclusive,
Mhm.
what did you have to do then? Didn't you have to go back and do another test?
Yeah.
So now, I know 2 places that are inconclusive. When x is -1 and when x is 1. Let me put that stuff in and just look directly at what I get. That's obviously convergent.
Yeah.
Alternating series test, right? So this, I can make like that. Watch this, everybody watch. Bam, okay. Right? Because that -1, it converges. What if x is 1? What happens to this poor little dude?
Convergence.
Why?
I'll just use our comparison. It looks like harmonic, so.
Yeah, 1/n basically is what it is. Harmonic, so it's going to diverge, so that, I'm going to leave it like that. What's the center of this interval? What's the center of this interval from -1 to 1? What's the center?
0.
0. What would you say the radius of the interval is then?
1.
1, because isn't the radius from the center out to either side? So there's something called the radius of convergence, which is literally just that. How far from the center do you go to the endpoints? You guys all see that? Whatever the center is. So we call it the radius of convergence. Where am I going to put this shit? That should go away. Radius of convergence equals 1, and the interval of convergence is -1 inclusive, 1 not included. So the rock and the IOC, right? You guys get the feel for that? So it's exactly like what a radius is on a circle. It's the center out, either way. So the radius is 1, and the interval is just rewriting what we got here in interval notation. Interval of convergence. Okay, I like it. So it just takes the ratio test and applies it in a situation where we haven't identified what this base is. And mathematically, it makes sense. If you were going to make a problem, if I was going to make you make a problem, and I wanted it to look like this, you want it to converge, you know what number to put there. Right? Not a specific number, well, what kind of number? You know it's got to be less than 1. Right? Now, whatever Cn is can certainly affect things. Yes? And does the center have to be 0? No. All right, so let's look at a few more examples. And let me make sure I'm not forgetting anything, because I like to get to the meat and I forget little details. Okay, beautiful. We're right on track. Kicking the ass in. Yeah, let's do that one. I like that one. Okay. So let's do one where the center is not 0. And actually, well, not the center is not 0, but yeah, center is not 0 and the radius is not 1. Yeah, let's do it. Okay. So what I like to do is I like to ask you, I give you a series, I ask you what Cn is, and then I ask you to tell me what the interval and radius of convergences are. So let's see, what about this guy? Actually, a really good first question is this even a, that's better, Jeff. Is this even a, what do you call it, power series? And it is, it's just a shifted power series, right? It's just been shifted, +3, exactly. So you see how the center is going to be 3 now. Right? In fact, I really want you to hear this. If x is 3, what happens? So for any power series, let me write what a real power series kind of generally looks like. Here's the real general form of a power series, right? No. There we go. Oh, where 3 came from. Do you see, if x is a, whatever the hell a is, doesn't this make a series of nothing but what? If x is a, what's that?
0.
0. So, do you see how this will always converge? Any power series will always converge for at least one value of x. Whatever makes the little thing 0, right? Because then every term is 0. So, in mathematics, we very often call that the trivial solution. It's like the duh solution, right? You guys coming with me? So if I said, what makes this equation true? The trivial solution is x equals 0, yes? But then could there be other, in fact, how many other answers are there? You guys know? Anybody? How many other answers besides 0? 0 is the trivial solution. How many other solutions are there to this? You know this one. There's 11 total. We got one already. So there's how many more? 10. They could be real or complex, right? I love it. All right, sorry. Again, a little tangent. I'm sorry. Okay. But the idea of trivial solution is bigger than just this, but this would be the trivial solution. So every single power series is convergent at least at one point, the one that makes it frickin' 0. Everywhere, right? And then the question is, how far can I get from that center and still converge? Does that make sense? No? Yes?
Yeah.
Okay. So like the first one we did, this thing, the center was 0, and we can get up to 1 and down to -1, right? But then there could be differences in Cn and differences in x minus x plus that could kind of push that out or push that in. Or maybe even just it only does it at one place. Okay, so let's look at this thing. Somebody tell me what is Cn? 1 over n, two cats. Right, it's the part that's in front of the x minus a to the n piece. Step A is easy. Step B, figure out the radius and interval of convergence. Do it. I'll wait. Please, dear God, if you have any question about this, ask immediately, right? Don't just let me steamroll you. I don't want to do that. Some of you guys look very angry at this problem. I'm sorry. At the problem? Well, good point. Well, I could be the problem, so. They're like, yeah, math boy, make a joke, but you are. Hopefully that's not what's going through anybody's head, but. Okay. All right. Like you tell. Yeah, exactly. Yeah, you better walk fast to your car. Okay. I'm gonna start to catch up to you. Very cool. You see why it can't be 0, of course, right? For this specific one? Okay. So this sets up so crazy nice. It's just same form, increase n by 1 times the reciprocal of that, right, if it's a fraction. What's this limit here? 1. Yeah, so always look for those. Always look for your polynomial in n, because then it's the question about degrees. Quick, get those done. Get those out of the way. And of course, these, how do they? What am I trying to say? How do they reduce? Yeah. Of course, that limit is x minus 3, and again, people get confused here because we're used to getting a number and looking to see if it is less than 1. Now we kind of impose that. We're like, okay, I want this to converge, so let me make this sucker less than 1, because then I know it converges, right? I really want you guys to see that, because I think some people get a little confused right there. They're like, how do I know if that's less? No, you make it less than 1, and then you make it tell you when is it less than 1. All right, so then I get x minus 3 between 1 and -1. So the next is between what and what? Add 3, right? 2 and 4. I love it, right? So the radius is still, for this one, but the interval will be more interesting. So the radius of convergence, what's the radius? What's the center? 3. We knew that from the beginning. So what's the radius? 1. from the center to either side is 1 away. And what's the interval of convergence? Why do I not know yet? I don't know what the interval of convergence is yet. Why not? What have I not checked yet?
So,
When is this thing inconclusive?
at 2 and 4.
When this equals 1, which means the endpoints have to be checked. I know it's good for everything between 2 and 4. The test is inconclusive for the endpoints. So just take a minute, rewrite that if x is 2. Let's see what you end up with. Yeah, do that. Oh, that's beautiful. Let's see. Ooh, yeah, let's do that one. I have a good idea. So if x is 2, I really want you guys to see every step of this and why it makes sense. So this less than 1 means it definitely converges. Equal to 1, I don't know. I have more work to do. Shit. So every time you do one of these power series, finding the interval of convergence, radius of convergence, you have to check the endpoints. What kind of series do they make? Can I just see if it converges or diverges? You're hoping, right? Or else then you have to do a test. So if x is 2, what kind of series do I get? What's it look like? Yeah, because up here you're gonna get
-1 to the
negative 1 to the end.
times 1 over n, or
I'm with you. And this does what?
that would converge.
Converge, yeah.
Conditionally, or, yeah.
Yeah. Now, if x is 4, what's true? I think I heard somebody's, it would just be 1 over n, right?
Yeah.
And that, of course, does what?
Diverges.
Diverges. Either p series or it's the, what kind of series? Harmonic. So then what should my interval really be? I want to include 2, not include 4, so it'll be 2, 4, bam. Become a number 4. There we go. So if I want to make a problem look like this, what number can I put in for x and have the answer be convergent? Anything from that interval. This is not true, but I want you to understand, this is sort of like a domain. Isn't this the values of x that make this work?
Yeah.
In a way, right? Doesn't let it go freaky. So isn't that sort of like the domain of this weird new power series function that we've never seen before? It's just another kind of function. Yeah, maybe. Not too bad, right? I mean, if I were you, ratio test. If I were you, I'd feel pretty good about ratio test compared to some of the other stuff. Yes? And then this stuff is built right onto the ratio test. It gets a little weird at the end, but it's still the same. You still, whatever you get's got to be less than 1. And you impose that restriction on it. Okay, maybe. All right, let's do a really freaky one. They're too nice to you. Let's see. I like this one. Yeah, that's really freaky. Okay. Yeah. So identify Cn, and then I want you to find the radius of convergence and the interval of convergence.
Is this square root of n plus 1? Is that 1?
Yeah, it's a 1, sorry. So, yeah, that's a 1. Is that the question?
Yeah.
Yeah, it's just a 1. Yeah, here it is. that's boring. Like that. Maybe, yeah.
I didn't get my exam.
Oh, wait, so that's the stuff people turned in. What's your name?
Hayden.
There you go. So let me know if all this makes sense. Catch up to you guys real quick. Absolute values, you can ignore the negative. Is that cool? Just, yeah, it's absolute values, so don't write the negatives down, that's silly. So what's, now I want you to notice something. I don't know if I've told you this directly, but remember, of course, we talk about pre-calculus, we keep talking about the degrees, and then it's the ratio of the coefficients. So for example, if I had the limit as n goes to infinity, let's do something different. Square root of 4n squared minus 7 over the square root of n squared plus 2. Let me ask you a very interesting question. What's the degree of the top?
1/2. Wait, actually.
Just one.
First degree.
Oh,
What's the degree of the bottom?
First degree.
First degree. So the limit should be the ratio of the coefficients of the highest degree terms, right? Like always. So what's the limit?
4.
No.
2.
Yes, 2.
Oh,
Oh,
shit.
2.
Square root of 4.
Oh.
The square root of 1, right? The ratio of the coefficients, square root of 4 to square root of 1. 2. So what's this limit here? 1. Yep. Just when you have square roots or cube roots or whatever, you actually have to cube, if it's like 2 inside and it's cube root of 2 or something, right? You guys get that? So like for example, if I had limit, I go to say cube root of 5 n to the 4th plus 2 n over cube root of 7 n cubed minus, or the plus 6n to the 4th. Okay. Sorry, so I'm very excited about this. There you go. Degrees are the same, yes? I don't care where they are, but the degrees are 4/3. So what's the ratio of the degree of the coefficients?
5 over.
Cube root of 5 over
Root of 7.
cube root of
6, my bad.
6. There we go. So cube root of 5, 6, and you can rationalize out your shit. Yeah, okay. So you can extend. In pre-calculus, you only care about truly rational functions, which are ratios of polynomials. So that's the only thing you ever talk about. But then you can extend this degree idea to things that are radical, right? Totally. Okay. And then, are you at the point where you know what's going to happen with those?
3x. Yeah.
What do you get?
3x.
3x, yeah, you just lose n of them, so you get one of each left. And that's got to be less than 1. How do I solve that shit?
X divided by 3. Or y.
Yeah, you can divide by 3 right now, or you can divide by 3 after you break it up, but I like to divide by 3 right now. Alright, is that cool? Because 3 is positive, so divided by 3 doesn't affect the absolute value or the inequality. You guys with me? And then what's the interval look like, or the inequality?
1/3. 1/3.
Like it. Okay, let me stop for a minute. So now we finally get 1. The center is still what? 0, but now the radius is 1/3. So the radius, was that wrong? Radius is now 1/3. And the book uses a big ass R just to let you know for the radius of convergence. I don't know why. It's just- And again, why do I not know what the interval of convergence is yet? Because I haven't
Check.
checked
And the one.
endpoints. I love it. Yeah. So go ahead and take a minute and check the endpoints, please. Be really careful when you do this, by the way. You have to look at the original, so the negative comes back, right? You have to look at the original series. This was work. This is the series. If you let x equal -1/3, that's going to do something. Sorry, we had a hand up?
Oh, so it's already, you said it's 0, right?
Yes. And we knew that from the beginning, because this is not shifted. So I knew the center was gonna be 0, but then you can really see it here. Yeah. So let's see, if x is negative 1/3, what happens to this thing? We get negative 3 to the n times negative 1/3 to the n over this. What happens here? Here. It's just 1. It's just always 1. And what's true about this series?
Convergence.
What kind of series is it? Trying to be?
It's a P series.
P series, where P is
1/2.
1/2, which is
Divergence comes.
less than 1, divergent, right? This is where things are gonna suck a little bit, because changing gears sucks. So with the ratio test or a geometric series, what's gotta be true about L or R? It's gotta be less than 1, right? Absolutely. For P series, what's gotta be true about the power?
Greater than.
Okay, so you gotta keep that straight. So ratio and root test are both based on geometric, that's why they all have the less than 1 thing, for the exact same reason. P series is its own deal, right? So this diverges. Without doing any of the writing up here, can you guys tell what's gonna happen if I put a positive 1/3? What would stay alive? The alternating part, so this would converge, because then you'd have limit 0, positive, decreasing, all that kind of shit, right? You guys see that? So now I get this, so the interval convergence would be, don't include negative 1/3, but do include positive 1/3. Okay. Let's do one more quick one, and then let's do some calculus to some freaking series. Because we are in calculus class after all, let's do some of that. One more quick one. If I had, I don't know what number I want. What do you got, Jeff? Sure. This. Even before you do any work, do you understand, will any value of x besides 0 save this? Do you know what I mean? Like, what is n factorial doing? Just getting stupid big, stupid fast, right? No matter what number I put in, for x is 1 over, let me pick a different, 1 over 38 trillion to the trillionth power to the trillionth power to the trillionth power. I don't care, this thing is eventually gonna be bigger than that. Right? So I know ahead of time something that this should have a very small radius. So let's see what happens. So this will be n+1. This is a weird example where it's not a fraction, right? So I can just directly do this. Finally, right? It's not fractional, so I don't have to multiply by the reciprocal. I can just make the ratio directly. And I'm just going to do this real quick. I get an n+1 left over here, right? I get an x left over there. So what's that limit?
Infinity.
It's infinity for every value of x except 1.
0.
0. I love it. Now, I want some of you guys to object. Will anybody object to that? Yes?
Because can it be indeterminate form, right?
I love it. Okay, beautiful. Okay, how do I say this? No, but I totally wanted somebody to say that because that's what it's freaking telling you the whole time, right? So I really want you to understand. This definitely goes to infinity. And I just said if x is 0, this limit is not infinity, it's actually 0. And a beautiful response, and a response that I would want to get from a calculus student is, Jeff, what the shit, do you know calculus? You know, I'm glad you didn't say that. Infinity times 0 is indeterminate, man. What the shit? So here's the, does everybody understand that? Okay, so I really want you to understand why that's not this situation. Oh shit, well that we didn't even, okay. Why am I using this thing? I don't know. Okay, if I said, find the limit of, in fact, let me do this. Find the limit as x goes to 1 of natural of x times 1 over x squared minus 1. I love it. What form is that in? You can do it. At 1, what's natural log of x?
0.
0. What happens when I put a 1? Try to put a 1 in there. This goes to
0. Oh,
the bottom goes to 0, so the whole thing goes to.
Indefinite.
When I put a 1 in the bottom, I get a 0 on the bottom, so the whole thing goes to 1 divided by very small gets very big.
Yeah.
So the whole thing goes to
Infinity.
infinity. I love it, right? Isn't that 1 over 0, basically? Yes? Okay, okay. That is indeterminate. I'd have to do, and that's, of course, L'Hopital's would just eat that up. Yes? Because then I could put that on top, and then it would be infinity over infinity. L'Hopital's would eat it up. Everybody's cool, right? What? So that's if I give you like f of x equals that, and I want to know the limit. What if I tell you f of x equals, what do you got, Jeff? Let's say, yeah, x plus 1 times 0. What's the limit as x goes to infinity of x plus 1 times 0? And here's the difference. And this first guy, is that ever equal to 0? When is that equal to 0? When x is
1.
Do I ever get there?
No.
All right, so is this actually ever equal to 0?
No.
Never. Is this actually ever, infinitely big? Of course not. Right? Infinity is not a location. Okay, maybe. And this one, this is always 0. So this is kind of silly. What is every element of this? I don't care. If x was 1, what is this?
0.
If x was 2, what is this?
0.
If x was 3, what is this? All right, so for every value of x, it is 0. So this limit is 0. So indeterminate forms, why did L'Hopital's rule work? Because it's all about who's getting where faster, right? If the bottom is going to infinity faster than the top, and you should all be able to say, yes, definitely that's getting to infinity faster, this limit is 0. If the bottom is getting infinity slower than the top, infinity. If the bottom and the top are going to infinity at the same rate, you get numbers like E. Or any 7.289 or something in the middle. They kind of agree. Neither one of them outpaces the other one. You guys understand? So in this example, if x is 0, every element of this is 0. So of course it converges, right? And for the limit, if x is 0, this is basically this. Yes? Every element of this is 0. So of course the limit, if x is 0, this limit is 0. Okay. Maybe? Oh man, you guys look beat up. I'm sorry. Does that make sense? Yeah.
So basically, what do you call it? So like how you're saying, it's like the ln of x is just like a competition of like two infinite
Yes.
numbers.
Yes. This is going to, I'm sorry, I didn't mean, I meant, yeah, no, I see. Yeah, this is going to 0, and so is this. So I didn't mean infinity when I was talking. I forgot what I was doing. So this is going to 0 and this is going to 0. If I put this on top, right? Okay, so it's a competition between who's getting to 0 faster. So let me say this better this time, because I forgot to let it go to 1. If the bottom's going to 0 faster, then the whole thing's going to infinity. If the top's going to 0 faster, the whole thing's going to 0. If they're both going to 0 at the same rate, then it's actually going to be the slope will be the answer, which is why L'Hopital's rule works. It's all about how fast, which is the whole idea behind L'Hopital's. Derivatives are how quickly shit's happening, right? That's why L'Hopital's rule kind of like just fundamentally makes sense that the derivatives will come into play. Okay, maybe. But here, this, if x is 0, it's at 0 already. It wins. How fast was it? Infinitely fast. It was there. You're there, right? So that'd be great. I'm like, no, I'm not. Okay, right? Unfortunately, we can't teleport yet, or time travel, right? Or maybe that's for the best. Seen too many movies. All right. For both of those situations, teleportation and are you guys okay with that? Do you guys really understand? Limits where you have functions that are approaching 0, they're just never equal 0. So then it's about who's getting there faster. If I freaking make the value 0 from the beginning, it's 0. There's no question. I don't give a shit how quickly this thing grows. This is already at 0. It's never going to win. It won. The 0 thing won. So for any other x besides 0, this is infinity. Whatever number that is, if that's a number not 0, this is infinity, no question. If x is 0, then the limit's 0. What does that mean? Now finally, oh my God. If we can actually answer this very easy looking problem. What does that mean then? This is only convergent for what? If x is 0. What's the radius then? 0. What's the interval of convergence? 0. It's not really an interval then, it's just a set containing 0. Not the null set, because the null set is an empty set. Yeah, this is not empty because it has a 0 in it. Right? Yes.
So when the limit is 0, we don't have to check for the endpoints, right?
Yeah, well, if the limit is infinity,
Oh,
then there's no endpoints, but also if the limit is 0. So let's do, shoot, what time is it? Yeah, let's do, I don't think we've seen a limit equal to 0 yet, if I remember correctly. And that would be something like this, very quickly. This is going to be a very, 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 anyway, you're going to see that series again. It's going to mean something different to us very soon. It's going to be so cool. Okay. Right now, it's just a freaking series. We've seen this before. I'm almost certain it's been in the homework before, right? This type of form. But now, if I do this ratio test real quick, so now I lose n x's, so I got an x. I lose an n factorial, so I'm left with an n plus 1 on the bottom. And of course, no matter what number I make x, what's this limit gonna be? As n goes to infinity, whatever constant's on the top,
0.
it's gonna go to 0, right? Whatever number you can imagine that's really big, I can make n bigger than that. Nah. If I just make n equal to the number you imagine, then the bottom's bigger than that. Right? So this is going to go to 0. Now what does that mean? When is that less than 1? When is this less than 1? I love that question. When is this less than 1?
Always.
Every other Tuesday? Yeah, always. Always, right? This is always less than 1, so it doesn't care what x is. X could be anything then, yes? Whatever the shit I make x, this thing is going to make the limit 0, which means this is going to converge. And we kind of knew that from the beginning. This is n factorial. This is just a number to a power, right? Ain't no way this is going to keep up with this guy. I don't care what you make x. Because again, we're going to infinity. So you're like, I'm going to make x 18 trillion to the trillion to the trillion to the trillion. All right, we'll just go out until n is way past that, and then you're, right? Does that make... Yes.
Sorry, can you just show how you got from the
Oh yeah, so
yeah,
you
that one to
lose
that one.
n x's, right?
Yeah.
And then
You have one
here,
x.
this is n plus 1 times n forever.
Yeah. Oh, okay. Then you cross out the n.
Yeah, so
okay,
then you
there
get n plus 1 forever, yeah. So I want you to get to the point, you don't have to be there yet, but you do, the more you do of these, the quicker you should be able to, you shouldn't have to rewrite them, you should be able to get to the point where you're able to tell what's gonna be left over. And again, you don't have to be there yet. So you can show yourself, you can do one more step than I did, kind of break things up, right? No problem. So what's the interval of convergence then? And what's the ratio, let's do the radius first. All right, this is weird. So when is this less than 1? Always. Doesn't matter what x is. So what could x be? Doesn't matter what x is. So what could x be? All real numbers. So the interval is, so what's the radius? Infinity. Okay. Let me put a little r in there to make it the textbook have. So if the Cn itself goes to 0 fast enough that it doesn't matter what you make x, then x could be anything. That makes sense. This is like a function having a domain all over the place, right? Isn't this, so this is like one of the most basic power series. And it becomes one of our most basic and loved. Can anyone tell me, like, calculus? What function would you like to do calculus to? Like derivative, integral. Even better than polynomials. Sorry?
E to the
E to the x, right? You integrate e to the x, you get,
e to the
you differentiate e to the x, you get,
e to the
holy shit, right? Of course. So we're going to prove eventually that this is e to the x. Just to give you a little teaser. We are going to prove that e to the x is this infinite sum. And what values of x does it work for? All of them. Why would that make sense? Because e to the x is a beautiful, nice, simple, beautiful little function. It's so nice. So of course it's going to work everywhere. It's just the way it does. It's just nice. Yes. So.
Oh no, sorry.
Okay.
Question?
Yes.
So Cn in this example is 1 over n factorial.
Beautiful. Yes. So you start to see how your Cn could have huge effects on things, right? So at the very beginning when we did this, I almost felt for sure you guys were like, Cn doesn't matter that much, you know. But now you see, it depended on what Cn is. It could either be, you know, only one thing works, or every damn thing works, right? That's the only difference between these two, isn't it? Cn here is n factorial. Cn here is 1 over n factorial. And totally different domains for both. Okay, I like it. Okay, boring the shit out of some of you, which is fine. I can deal with that. It's better than A. Okay. Okay. So, last thing I want to do, like I with this, before you get too excited, is some algebra. No, calculus. What is some calculus good stuff? So watch this. So we know from before, the only power series that directly relates to a function that we proved, can't use e to the x, we haven't proven it yet, was this guy, 1 over 1 minus x. If x actually value is less than 1. What does this equal? Anybody remember? What's the infinite polynomial?
1 plus x plus x squared.
Okay. Right? Okay, let's try something interesting. This is kind of cool. Is everybody cool with this? You were all here when this happened. I really want you to understand this. If x, absolute value of x is less than 1, this function is equivalent to this function. I know I've said this before, but I really want you to understand. True. If you go to the infinite place, this value will equal this value. And we did in a specific example earlier. In fact, let me see, last script. So do me this favor. Can you all take the derivative of this side? Okay. In fact, before you do it, sorry. Let me make this even better. Write this in summation form for me. What's it look like? Nothing too bad, right? What's this in summation form? X to the n, right? Okay, take the derivative of this side from me. Oh, wait.
Negative natural log of one.
Well, you integrated it.
Oh.
Derivative. Take the derivative. I said derivative, right? I didn't want to integrate that. Okay. Who's got that? So remember, you can write this as 1 minus x to the negative 1, right? So then the derivative's pretty easy. What do you guys get?
Is it negative 1 over
I got positive
1
one
minus
over
x?
So let's see. The negative 1 would come down, times 1 minus x to the negative 2, times chain rule.
Yeah.
So it should be positive 1 over 1 minus x squared. I love it. Does everybody see that? Negative 1 comes down, negative 2 power, but times the derivative of the inside, so the negatives cancel. I love it. Now, you guys did the derivative of this side. So how do I make this equation still true? I have to take the derivative of that side. Do what your gut says to do. Do it. Follow your gut. Not something a math teacher says often enough, but so I'm taking a derivative of both sides, so we maintain the equality. So what happens on this one? Yeah, the n comes down,
and there's n minus one.
x to the n minus 1. Now here's something funny. I don't have to make this n equals 0. In fact, we normally don't, because n equals 0 would result in a 0 term. Do you guys see that?
Mm-hmm.
It's actually a little bit more, it's worse than that. So what we normally do when we take a derivative is that goes up by 1. Sometimes it's just because if I leave it at 0, the first term's 0, who cares? Right? But other times it's actually because it makes the first term undefined, so we have to get it out of the way. That, we just took the derivative of an infinitely long polynomial. Do you guys understand what just happened? We just did the derivative of this. What's the derivative of this?
0 plus 1 plus
Yeah, 0 plus 1 plus
2x,
2x plus
3x squared.
3x squared. And you see how the 1, 2, 3? 1, 2, 3, right? You guys see what's happening? I really always want you to understand concretely what you just did. So when we take a derivative of a series, so far, we've done one problem, and it was x to the n. But it was pretty easy. It's basically like taking a derivative of anything. It's almost too good to believe. But even better is, we did an infinite number of terms. Bam! That kicks some ass. Yes? Okay. So what we just figured out also is, here's a function, here's what it looks like as a series. Here's another function. We built it off of a known series. Hey, there's what it looks like as a series. Couldn't I integrate this if I wanted to? And then I would integrate this side. Ooh, shit. Right? Okay, let's try that. So let me write this again. No x. Okay. So we integrate. Indefinite. Some of you guys are going to mix this up with integral test. No. We're just integrating both sides, just like we took the derivative of both sides. So it has nothing to do with these limits. This is a function of x, I can integrate it. This is a function of x, I can integrate it. Ally is a little ahead of us now. So what do you get when you do this?
A negative natural log.
Yeah, negative natural log.
Absolute value
Yes.
minus x and plus c, or
Kick ass.
plus
Plus
c.
E. Now, integrating this, let's see what happens. Well, we'll leave that for now. What happens inside?
The m comes down and.
No, we're not taking derivative.
X to the n plus one.
Yeah, x to the new power, it's always raise the power and then divide by the new power, right? Let's see what happens. Let's see what happens. Let's kind of see if I leave it 0. Okay, let me see. So remember, this is what it really is. If I integrate that, what do I get?
X.
If I integrate, I get x plus
X squared.
1/2 x squared, right?
Yep.
Plus 1/3 x cubed. Do you see how the bottom, if I start at 0, the bottom goes 1, 2, 3, right? Do you see what I'm saying?
Yeah.
And the powers go the same, 1, 2, 3, right? So it does want to stay at 0, right? And then I would have this, whatever this plus c is. So then, the c's kind of cancel, I get this function has a power series representation like this. Let me see if you, let me push this one step further. Okay. So what we're doing at the moment is if I have a known power series for a function, so a function, and I know what it looks like as a power series, I can do some calculus to both sides to create power series for other functions that are based on this. So I can get the power series for that, I can get the power series for the natural log, blah, 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 blah. Okay. Maybe. And by the way, do you remember if you could bring this negative up as a power, right? So this will be like this. Is that cool? These are the same things, yes? Because a negative coefficient can go up as a power, so that'll be 1 over that?
Yeah.
Okay. Freakadelic. So it's kind of a coincidence that it's a natural log of the original. Yeah. Okay, maybe. Okay. All right. One more thing to look at. We're gonna just milk this for everything it's got. So here's what this is. And just remember, for every power series, for each of these, they kind of inherit the domain. So we have to remember, for any given power series, it's got a certain domain. So every power series we create and look at is going to have its own domain. And how do we figure out what the domain is? We do the ratio test, right? What do you think this is going to be? How does that relate to this? What form is this? This is one, any value I put in for x, it's 1 over 1 minus something, correct?
Yeah.
Okay, so what is this 1 over 1 minus what?
Minus x.
So that would mean, if I put a 2 here, wouldn't I put a 2 there? If I put a 7 there, I put a 7. If I put a 1/3, I put a 1/3, yes? Now, of course, what I just said was wrong because I can only use values less than 1, but still, it's the same idea. So if I put a 1/5, I put a 1, blah, blah, blah. So what did I put here?
A negative, negative,
So what I put there?
negative.
That, what we just did, seems too easy, but it's so beautiful. It's exactly how functions work, yes? If I know that f of x is sine x, what's f of negative x? So you just replace x with negative x, don't you? That's how functions work, right? And of course, you can do more shit with that, who cares? So what's a better way to write this, to capture what's really going on?
Negative 1.
Negative 1 to the n, x to the n. Okay, so what about? All right, 2 more. What about, we start numbering these. Why all of a sudden? I don't know. What about 1 over 1 minus x cubed? Yeah, what about 1 over 1 minus x cubed? So it'll be, you just replace x with x cubed. Yeah, so you get x to the 3. So again, power series, new to us, but they are basically functions of x. Whatever functions of x do, they will also do. So if I put f of x cubed, I would just replace x with x cubed. Exactly what the shit happens here. It just almost seems too good to be true. And actually, I don't know what you guys think, to be honest. This is all new. You don't even know what's too good to be true, what isn't. You're like, oh, right, it's all stuff. Okay. What about this? What about x over 1 minus x? Oh, shit. Oh, shit. Let me do one thing. Let me rewrite the question. This is x times 1 over 1 minus x, correct? These are the same? Well, what's 1 over 1 minus x? How can I write that?
X to the n.
Yeah, sum of x to the n, yes? Now what do you think happens here? What's the series see as a variable? The summation symbol sees what as a variable? This is going back to calc 1. Obviously, what's the variable in terms of the summation symbol? What's it see the variable as? N. So x is a constant as far as it's concerned, yes? I don't know if you guys remember that. We needed Riemann sum stuff. You should have done a little bit of manipulation of series. If you didn't, go back to your calc 1 teacher and say, what the shit, man? Because they're supposed to kind of get you ready for this a little bit. So I can bring that in. So then what's that become? X to the multiply by x. N plus 1, you get 1 more x. So this series, this function, can be represented with this series. And why was it so easy to find? Because it's based on a series we know. So we've taken a huge step today. We kind of backed our way into realizing that a series can be written as a function. And that's that a over 1 minus r. That became 1 over 1 minus x for the specific power series we set up. But that is a function. 1 over 1 minus x is a function, and I could write it as an infinite polynomial. So 11.8 is the basics of power series. 11.9 is the stuff I'm doing right now. It's the calculus manipulation of it. Let me see if there's anything weird. Oh. Blah, blah, blah. Oh, okay. So let me ask you this. Here's a question you would see in the homework. In 11.9, right? The power series representation. Oh, it's a long word. Natural log of 1 plus x. Now, in 11.9, the only power series we know is 1 over 1 minus x, right? So your task with these kind of problems is, what calculus relates this question to the only thing I know? Calculus and substitution stuff, possibly, right? So what calculus could you do to natural log to instantly make it look a lot more like this? Derivative. So what's the derivative of this? 1 over 1 plus x. And that, of course, is 1 over 1 minus the thing we just did, right? So in this section, when they say, find the power series representation of something. Okay, is that an integral or a derivative of something related to the only damn thing we're allowed to know in this section? So if I write this power series for this, what am I going to have to do to that to get this? Integrate. This is the derivative of what they want. So if I write a power series for this, which we did earlier, we did exactly this, then I have to integrate it to actually answer the question, right? Do you guys see that? You have to figure out the path you got to take to get from what the hell you know to what the hell they want to know. So what was this?
-1.
Okay, so now integrate both sides. So this, of course, is this. Don't worry about it, this is just the constant, right? According to the integral, this is a constant. Doesn't care about it, it just comes with a ride. That's not too bad, right? What do you guys get? This comes from the ride, and then what does this become?
X to the n plus 1 over n plus 1.
Yeah, and the plus c's cancel. Cool, maybe. Very new shit, right? It's now you kind of see why the entire part of chapter 11, to be really honest, is just getting us ready for what we're about to do. And so is this. This is just getting us ready for the main topic, which, to tell you honestly, is section 1110. 1110 is what everything is kind of getting us towards, right? This has all been baby steps. Not really. I don't want to make you feel like this is like, adult. This has all been learning to ride a motorcycle. There we go. Better baby steps. Let me see. I don't think I want to try to shove too much else in. I want to remind you guys, and let me know if this is not true. We have an 11.8 worksheet, 11.8 handout, and on the back side, it's 11.10. Does anybody still need that? Okay. Let's do this. On the 11.8 side, let me let you do one of those problems. Do number 4 at the bottom of the 11.8 side. I don't know why I didn't make an 11.9. I just didn't. We'll do this, and we'll do one more quick thing, and then we'll call it a night. So this limit of the end stuff,
1.
this is 1. Here I just lose n of these, so this is just gonna be, just to cut to the chase, x minus 5. Is that cool? And that has to be,
What's that?
that's the 1. So I know this is gonna be,
4, 6.
yeah, so the center's gonna be 5, so it's gonna be 4 to 6, and then I have to check endpoints. And again, if you have any trouble, you write this, and then you add 5 to all sides, so you get to 4 to 6. So notice the radius doesn't change. The radius is 1. I don't care if I include or exclude the endpoints, because if I add 6, that doesn't add anything, because there's an infinite number of numbers between it and so the radius is still 1 no matter what. But if I plug a 4 in, let's see if we can do this really quickly. If I plug a 4 in, it's alternating, correct? But if I plug a 6 in, it's not alternating, but it's still 1 over n squared, which is convergent p series. So I'm going to include both. So the interval of convergence, 4 to 6, and the radius of convergence is 1. So the last quick thing, and funny I'm saying quick because this is everything, but here's a power series, right? And let's write out the elements to this, just to be really thorough. In fact, let's make it even more, there we go. So wouldn't this be C0 times 1? Is that cool? Where n equals 0? So C sub 0 just means the 0th constant element, because it's dependent on n. I just don't know what the hell it is, right? Anybody at home, I'm sorry. I haven't been moving this at all. Plus C1, x minus a to the first, plus C2, x minus a to the second, plus so on, right? Pretty straightforward, yeah, because there's an n there, there's an n there, blah, blah, blah. All right, now watch, this is kind of cool. What if I wanted to, let's do e to the x. Let's say I want to know what the power series representation of e to the x is around, let's do around x equal to 0, or a equal to 0. Let's say a equals 0. So this is very much like linear approximations. Do you guys remember those? Except with linear approximations, you stopped at the first derivative. I really want you, do you remember, and you had a function and you had the tangent line, and basically it was the local linear approximation. Do you guys remember any of that? So is it kind of not smart for calculus teachers to use a freaking straight line for a stupid thing that curves? Of course it's not going to hug it for long. You're like, how long does it work really well? Just from here to here. Okay, good job. So if I used, instead of a line, if I use something that itself curved, shouldn't that be able to fit a curvy dude better, right? No? Do you guys understand? So if I had a function, well, here's e to the x. And if I try to fit this with a straight line somewhere, let's say it's 0, right? It's only going to work really well close to 0. It's going to quickly suck. If I go a little bit out, I'm like, oh, I was off by that much. And it's like, oh, good job. You know, it's about 3 miles that way, give or take 6 miles. Oh my God, that doesn't help. It could be backwards with this shit. Okay, you guys kind of with me?
Yeah.
So, if my approximating tool was actually curved itself, it'd have a much better chance to fit. So you can imagine a 2nd degree fit, immediately better. A 3rd degree fit, immediately better. And every time you extend the degree, this 1st degree matches the slope at that point. Let's see if you guys get this. The 2nd degree would match the 1st degree slope. 2nd degree means? Concavity. So the 2nd degree matches the concavity. The 3rd degree would match whatever the shit that is. The jerk in like physics, but I don't think it's on it. Right? It goes position, velocity, acceleration, jerk for this. And that was before. Anyway. So the idea is if I get an infinite thing, instead of stopping there, which is what linear approximations did, C1 then was f prime of a, the slope. Remember that? Okay, maybe. So look what we're going to do. In order for this to work, so I'm going to call this my f of x, and I want this to equal e to the x. So this means f of 0 has to equal e to the 0. Well, what is f of 0? And again, I'm sorry, let's rewrite this. Then we make by a 0. You with me? So let's do this. C0 plus C1x plus C2x squared. Is that cool? Because I made a 0. Okay. A could be anything I want it to be. In this case, I made it 0. Right? So what's f of 0? What's f of 0? If you make x 0, what do you get?
C0.
You get C0. So I know what the first coefficient element has to be. All right? So then what's got to be true? F prime of 0 has to equal e, the derivative of e, which is e to the 0 still, right? So this is equal, what's e to the 0? That's right, kids, 1. What's the derivative of this? So I got my f of x is C0 plus C1x plus C2x squared plus blah, blah, blah. What's f prime of x? This dies.
C1.
C1.
C2.
2C2x, right? Plus more shit with x's in it, yes?
Yeah.
So what is f prime of 0?
C. No. 2. No.
What's
yeah,
f prime of
C1.
0? Everything has an x in it, so it goes to 0 except C1. So then this is C1. Okay, what do I do next? F double prime of 0. Which in this case, again, this is an easy thing. Every derivative of e, this is the derivative of e, this is the second derivative of e, which is still e, right? So if I do a second derivative, what do I get? Let me do another one here. So I get C1 dies, 2C2 plus 6C3x plus more shit with x's in it, yes? So what's f double prime of 0? 2C2. So then C2 equals 1/2. So do you see what we're doing is we're constructing what each of these are going to be. We are constructing part by part what the series is going to be. So I wanted to show you, so now you kind of maybe understand what I said earlier. We sort of did it backwards with the 1 over 1 minus x. We sort of backed our way into it. And if I'm given some function like e to the x, then I've got to actually step through it. Now watch. Let's put this, what we got so far. We got 1 plus 1x plus 1/2 x squared. If I keep going, I'm going to get 6C3 equals 1, right? I don't know if you guys see that. So it'll be plus 1/6 x cubed. Well, isn't this over 1 over 1? Isn't this 2 factorial, 1 factorial, 0 factorial? What's 6? 3 factorial. Isn't this x to the n over n factorial? Like I told you it would be, so let's do this. That was quick, I know, I'm sorry. I just want to give you the idea. So what we're going to do next time, we're going to formalize for any function, is there a quicker way to do this instead of having to do each thing? There is a slightly quicker way to do it. There's a slightly quicker way to kind of put it together. So next time we're going to work on, given any function, can I find the power series representation of it? And how can I make this process more efficient? So that's what we're going to do next time. Okay. And that, like I said, is the most important section in chapter 11. And we're finally going to be able to prove my shirt after we do this. Yes. All right, guys.
So do you need corrections in
Two.
text too?
Yeah,
Okay,
I'm sorry,
cool,
yeah.
cool.
I was using from last semester and I forgot to change.